Our team has decided to make an automated gold panning device to replace the conventional handheld devices that are commonly used today. Our motivation was to take a process that is very time consuming and tiring and make it much easier. Our prototype will also seek to replace the large scale machines that are expensive and immobile. This prototype will be small and can be taken anywhere and will be very affordable to the average person.
Here is a video demonstrating how gold panning is done traditionally.
Well, since people started finding gold, I would imagine. And the big rocks you can just pick out. You know, you don't rush things, but don't take forever too. I've seen some people get a pan full of dirt and spend an hour with it. You know, you don't get anywhere doing that. So you got to be patient, but smart. And the gold should be down in the bottom of the pan and stay in the pan while everything else gets washed away.
So during the initial design process, we came up with a few design constraints. First, we knew it had to be lightweight since it has to be carried into wherever gold is being panned. Something too heavy would be inconvenient for whoever is using it. Next, it needed to move properly in order to pan for gold. In the previous video, the man fills the pan with rocks and dirt and slowly washes out the less dense particles until gold is left in the bottom. We decided on a 4-bar mechanism since it'll recreate that panning motion the best. We also had to make sure that the pan would tilt far enough for the light particles to be washed out. And lastly, we decided that the input motion had to be cyclical in order for us to connect a motor to it, and it may also reduce strain on the mechanism. So this is a basic overview of the manufacturing process. We first considered our constraints and designed a basic 4-bar prototype in SolidWorks along with a gold panning tray. And once we were happy with this design, we 3D printed it and assembled it using wood as the frame and hardware as the joints. And parts of this will be elaborated on later in this video.
Since we are using a 4-bar mechanism to simulate our motion, it is possible to do our kinematic and dynamic analysis on a 2D model of our system, such that finding information about our linkage lengths and transmission angles is much easier than trying to simulate a 3D system. Here's the resultant data from the analysis of the 2D system. The top left table shows our resultant linkage lengths that give us the optimal stroke and angles at the end points of our cyclical motion, such that gold would remain in the pan and any silt would leave the pan. The imbalance angle is a side effect of getting the stroke and the linkage lengths correct. We know our system is a crank rocker, which is what we want to be able to attach a motor hand crank to it because of our S plus L versus P plus Q calculation. Since P plus Q is longer and our shortest link is the crank or link 2, it is guaranteed that our system is a crank rocker. Along with this information, 4 points of interest are analyzed for their transmission angle and mechanical advantage. These are the minimum and maximum transmission angles and the endpoints of our stroke. Note that the mechanical advantage at our transmission angle max and min are both more than 1, but we cannot calculate this information for our endpoints of the stroke since 2 linkages in a row, which makes beta equal to 0. These numbers were all calculated using the equation shown in the top right. Here's the resultant figure from turning our 2D model and analysis into a 3D version, which can support the gold pan. Some additional mechanics are added to our 4-bar mechanism for stability and for mounting, such as in this case where the figure is to be mounted to 2 wooden boards. This is the result of transposing our cyclical motion of our 2D 4-bar mechanism onto our completed model. Note that the same 4-bar motion shown in the other figure is present in this figure, and that the system is operated in this example with the hand crank.
Simple geometry for the components were used to save time in the design phase and to cut down on the use of materials in the 3D printing process. Components with a flat surface ensure that the part will adhere to the printing bed during the printing process, which aids in keeping the dimensions of the printed parts accurate. Rounded corners opposed to straight corners are also very important as they increase the strength of the components at these points. Having the majority of the model's holes perpendicular to the flat surface plane helps decrease the use of support materials during the printing process.
As you look at the front of our mechanism, you can see the basic motion and the back and forth motion of the pan. You can see here that the user can stand to the side and turn a handle that is connected directly to the crank, and the crank does have a full 360-degree motion. As you look closer, you can see that all of the parts are connected simply by nuts and bolts. Every circular hole has a bolt going through it with a nut holding it in place. You can see where the user's hand is that you could mount a small motor and it can turn the crank instead of using a manual handle. As you come back around to the front, you can see that the pan goes far enough back to deposit smaller particles in the water out the front and then returns to a horizontal position. This is an exploded view of our prototype that gives a better view of how everything connects together. Through each circular hole that is connected, there is a nut and a bolt holding it together.
In the initial design stages, a circular pan was used to shift soil. On further discussion and research, the circular pan was not a feasible idea. The shape was not practical for automation, and it also requires finer controls to properly remove the soil. Besides the pan, the design of the mounting frame was also deemed unusable. The issues with the original mounting frame design was that it was disrupting the planned motion of other parts. Furthermore, the frame had clearance issues with attaching itself to the main body. Some viable design alternatives was to remake the mechanism with a gear system to better transmit the rotational energy from the hand crank to the shifter. A slider crank could also be implemented to shake the pan, removing dirt at a faster rate.
And lastly, some areas for improvement. Some modifications that could be made to the model are to downsize the parts or the materials required to ease production, to upgrade part quality, since the real model would have to deal with constantly being filled with water and other environmental effects such as weather or dealing with rocks and dirt, increasing the sifter volume to allow for sifting a greater amount of gold at a time, increasing the crank length and size to allow easier turning since less input force would be required. And some additions and replacements that can be made are adding a water supply. Since in traditional gold panning, you have to refill the pan with water. A constant flow of water could be just supplied straight to the pan. Or replacing the hand crank with the motor so that a person doesn't have to input any force at all and they could do other things or operate other machines at the same time.